Assalamualaikum and a very good morning to all students. Today we meet here again for our next video under Chapter 5 Memory for our Computer Architecture and Organization course. So I'm Dr. Shafi Fauzi Kamal presenting to you from UMP. Okay, so today we are on our part 2 of Chapter 5. So let's start our class immediately. So last week we introduced to you about I introduced to you about current memory technology that we have in the world, okay, and how they are divided into some characteristics, physical characteristics, and also functions. So today, okay, we are going to discuss regarding, okay, how do you classify those technologies? Okay, so you usually we design the memory based on uh, certain key features, which is like, for example, capacity, performance, access time, and also the cost. So major design objective of this memory system is basically to provide adequate storage capacity and then to end at an acceptable level of performance access time and at a reasonable cost. So it means that how big is the size, how fast is the memory, and how expensive it is. So you can have a trade-off among this characteristic, okay, in order to optimize the usage of those memory. Like for example, in case you want larger capacity but at a lower speed, you can have a cheaper hard drive. Okay, but if you want a very fast memory, you don't need that much capacity. It can be almost a mid-range price, like for example SSD. Okay, so these three elements is how you determine the necessity of your hard drives. Okay, so we usually have a hierarchy to determine which which memory technology that we need for our computer. So basically, this memory hierarchy, okay, so the memory unit, okay, since it's an essential component in any digital computer, since it is needed for storing programs and data, so not all accumulated information is needed by the CPU at the same time. So it is economical for you to use the low-cost storage device to serve as backup for storing the information that is not currently used by CPU. So in order for us to distinguish which one is less important, which one is more important, we will use the memory hierarchy. So the memory hierarchy actually, okay, is created due to the gap of processor technology among the years. Okay, so according to Moore's law, okay, so we have a gap of 50% of technology growth comparing from processor and memory. So how do you compensate, okay, the performance of processor, the performance difference between the processor and memory? Okay, we compensate it by using different kind of technology for different kind of purpose. So how do you address this gap actually? So how do you address this gap? Okay, utilizing the memory hierarchy. So basically, you put a smaller capacity memory type, but faster. Okay, which is the cache memories between the CPU and the DRAM. And then here you create a memory hierarchy. So based on the CPU, okay, which you have a memory register, you have a cache memory in the middle and a DRAM. So this is to compensate the difference in speed between the CPU register and also the RAM. So at the bottom area, we have the storage device type, like for example, hard drives, okay, removable device. So this one is much smaller, or much larger space, but way slower comparing to other memory type, like for example, RAM, cache memory, and register. So they become at the lowest point. And finally, this is where our input source is. Okay, so some of the input source also have a memory inside it. So this one is considered as the slowest one since they are the furthest away from the CPU. So this main memory, okay, they consist of all storage devices employed in the memory hierarchy actually consists of all storage devices employed in a computer system from the slow by high capacity auxiliary memory to a relatively faster main memory to an even smaller and faster cache memory. So this memory unit that directly communicate with the CPU, usually we call it main memory. Devices that provide backup storage are usually we call auxiliary memory. So when you talk about the memory hierarchy, okay, so the main memory occupies a central position by being able to communicate directly with the CPU and with auxiliary memory. So this is the main memory, okay, through an I/O processor. Okay, so we have the I/O processor, okay, which is the I/O module itself. Okay, so this main memory, okay, auxiliary memory cannot be accessed directly to the CPU. So in case you need to use any data from the auxiliary memory, they need to be transferred first to the main memory before being taken into the CPU. So in this case, okay, the memory is kind of like a little bit crowded since there's a lot of data being will be coming in and coming out of the main memory. So in case you are using a lot of using one program a lot of times, okay, like for example your Chrome browser, okay, your internet browser, okay, certain software. So some of them, okay, they put it into the cache memory so that the CPU access will not burden the main memory. They can get it faster at the cache memory. Okay, so this means that your CPU can work even faster without having to access the main memory all the time. So most of your CPU, if you buy AMD or Intel, they have this cache memory inside it. Okay, certain size. Okay, how many threads it has. Okay, so this is where the CPU comes in. So CPU and cache usually they are bundled as one component. Okay. So CPU logic is usually faster than the main memory access time, with the result that processing speed is limited primarily by the speed of main memory. The cache is used for storing segments of programs currently being executed in the CPU and temporary data frequently needed in the present calculation. So when you look at volatile and non-volatile, okay, so we have two types of memory, okay, like what I mentioned last week, we have volatile memory and non-volatile memory. So volatile memory, they need electricity to hold the data, and non-volatile memory, they don't need electricity to hold the data. Unfortunately, those who are close to the CPU, they are usually a volatile memory. So you need the power most of the time, which is not sustainable in terms of long-term consumer computer. So in this case, we have what we call non-volatile memory just to hold the data permanently when you're done with your PC. So this is what we call a secondary memory. So the volatile memory usually you have when you are doing some process within your computer. So this is where you have the random access memory, the RAM, okay, where data is used just to bridge between the secondary memory and the CPU. So example, okay, of the volatile memory and non-volatile memory. So let's just mention like you work on a table, okay, on a desk. Okay, you work on a desk and you have a cabinet full of books behind you. Okay, so the cabinet full of books behind you are what we call is what represent the hard drives. Okay, the secondary memory, and your desk is what represent the volatile memory. So anything you want to do your work. Okay, imagine that you are a CPU working on a desk with behind you the hard drives full of books. So you as a CPU, when you want to work on something, you have to put the books from your cabinet, okay, at the back onto your desk first so that you can work on the book at your desk. So this is what RAM represent to the CPU. Okay, it's like a desk for you. Okay, so you work on your desk, and once you finish working on your book, you will return that book back into the cabinet at the back. So this means that from your desk, it transfers back to the secondary memory at the end. So this is what is different between the volatile memory and non-volatile memory. So volatile memory, like for example your desk, okay, it needs to be it cannot be crowded most of the time since you are the one who are using the desk for a lot of things. Okay, So sometimes, okay, you have to lose some data to insert new data. So they keep coming and going. So this is not efficient if you have a lot of data at the same time to process. Okay, so you have to save some of the data that you have done doing something with it back to the secondary memory. So when you look at the memory hierarchy, so it's like a pyramid. So when you look at the top, usually they are very fast. Okay, they are very fast and they are very small and they are very expensive, especially if you want to make a big one. Okay, so when you have this at the top fast and at the bottom, usually they are very slow. However, they are very huge. You can store a lot of space and they are least expensive because this expensive is in terms of the size they provided, okay, according to the price. Okay, so when you decrease the memory hierarchy, okay, you decrease the cost per bit. Okay, the cost means that the least expensive means that the cost per bit of storage, but it decrease the cost per bit, but it increase the capacity. Okay, and then it increase access time means it is a little bit slower. Okay, they will be maybe a lot more slower comparing to the top. Okay, and then they are usually used less by the main memory or by the processor. So this means that they are decreasing frequency of access by the main memory and the processor. So less thing you use, you put it in the slower drives. Okay, the most common thing you use, okay, you put it uh, in the upper level, okay, like for example cache memory or RAM. So why do we need the memory hierarchy? Okay, so this is for so why there is a memory hierarchy? So memory hierarchy usually we use to have to analyze the relationship between the size, capacity, cost, and speed. So relationship in memory implementation means that faster access time, greater cost per bit, greater capacity, smaller cost per bit, greater capacity, slower access time. Therefore, computer system is equipped with a hierarchy of memory subsystem, some internal to the system, okay, and some external to the system. Okay. So one of the memory that is inside the memory hierarchy is cache memory. So last week I did not introduce to you about the cache memory. So the cache memory sits in between the CPU and the main memory. Okay, so I mentioned before as example, CPU is U and memory is the dash. So what is the cache memory? Okay, so the cache memory is basically a small cupboard under your desk. Okay, small cupboard under your desk, a small rack under your desk, or even your desk drawer. Okay, so anything that you use inside your main memory, okay, you want to use, they will put it into on your desk first, okay, for you to process. And this is your desk, means the main memory. Okay, so when you have finished something with main memory, okay, you want to, like for example, you think you will going to use it again later on, so it's on the KIV, you put it in your cache first, and when the CPU wants to use the same data, they can just refer back to the cache instead of the main memory, so it's in the middle. Technically, so okay, how does it work? So basically, when the processor attempts to read a word from a memory, a check is made to determine if the word is in the cache. Means that if they are looking for data inside the main memory, they check it first in the cache. Is it available or not? So if so, the word is delivered to the processor. If available, they will put back into the processor. If not, a block of main memory consisting some fixed number of words is read into the cache. Okay, means that if they are not available, they will refer to the main memory and take a block of the memory and put it into the cache. Okay, and from the cache they will use it. So this is one way of how you use cache memory. So cache memory is usually in level 2, okay, between the CPU and the main memory. So if you look at this figure here, this is exactly how many bytes they are storing right now. So usually in processor, they have 4 to 8 bytes. In level 1 cache, 8 to 32 bytes. Level 2 cache, 1 to 4 blocks. Okay, so 8 to 32 bytes is usually a one block. Okay, 32 bytes is actually one block. Okay, they put 1 to 4 blocks. And from main memory, okay, they have around, okay, 1000 gigabytes. So currently we have about the 16 gigabyte, 32 gigabyte PC. So other than that, okay, they will transfer according to this sector from the secondary memory. Okay, so this is how your main memory works with the cache memory. So when the cache memory, we look at the cache memory. So cache memory is not a big memory. So they usually just use to refer to certain area inside the main memory. So assume an access to the main memory cause a block of k words to be transferred to the cache. Okay, access of main memory cause a block of k words to be transferred to the cache. The block transferred from main memory is stored in the cache as a single unit called a slot, line, or page. Once copied to the cache, individual words within a line can be accessed by the CPU. So means that from main memory, they transfer one block into the cache memory, and from the cache memory, they line by line will be inspected by the CPU. Because of the high speed involved with the cache, management of the data transfer and storage in the cache is done in hardware. So OS does not know about cache. So this means that any OS is okay since the cache memory works according to the hardware. Okay, they don't have different management of cache according to different OS. So if there are 2 power of n words in the main memory, there will be m times 2 power of n divided by k blocks in the memory. Okay, so m will be much greater than number of lines c in the cache. So every line of data in the cache must be tagged in some way to identify what main memory block it is. So this is the relationship between cache and main memory. So let's go towards a little bit of detail. Okay, so usually in cache memory, they have several factors in cache design. First, the size. Okay, and then the mapping function. Mapping function is how they are mapped from cache towards the main memory. So they have 3 types: direct, associative, and set associative. And then we have the line replacement algorithm. Okay, so means that how they replace the line inside your cache memory. So they use certain algorithm. For algorithm here that I've given example: least recently used, LRU, first in first out, means the first data in will be the first data out in case new data coming in. And then least frequently used, the number of time it being accessed is less, so they will be removed. Okay, and then randomly removed. So this is an example of how they remove data from cache and replace with new data from the RAM. And then we have the write policy, which is the write through and write back. We have block, line size. Okay, and then we have number and type of caches, single or 2 level, and then unified or split. So let's take a look about one of the mapping function here. Okay, I'll introduce one first. Okay, so here is what we have, a direct mapping. So direct mapping, okay, so the main memory block is assigned to a specific line in the cache. Okay, so here I equal j modulo c. So where I is the cache line number assigned to memory block j. So example, if m equals 64, c is equal 4. So let's see, line 0 can hold blocks of 0, 4, 8, 1, 2. So here we have 4 lines, and each 4 lines they can hold 4 units. Okay, so they can hold 1 unit. So 0, 1, 2, 3. After finish first line, they will second line is 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 up until 64. So let's take a look at direct mapping first. So we have a tag identifier, line number identifier, and word identifier. So what exactly the tag identifier, line number identifier, and word identifier? So we have this figure here. So any memory address, they have a tag, line, and word. Okay, tag, line, and word. So this is example one block of data. Okay, one block of data. So here, okay, the memory address from the memory, okay, they will refer back towards, okay, like for example, if the request is memory address here, okay, so the tag will be compared from with cache first. Okay, if they are tagged from the requested memory address inside the cache, okay, the data word will be taken from the data inside cache. Okay, the data word will be taken from data inside cache. Okay, so the line is here representing which line inside cache the memory location is. Okay, the data memory data location is. If there are no data, the tag is not recognized inside the cache, they will refer back towards the main memory and take this one, okay, and put it inside the process under the CPU. Okay, so this one will take longer comparing to when they need from the cache memory. Okay, so that's why we transfer them into cache memory. So once they already finish with this by the processor, they will move it into the cache memory. Or sometimes they will move it first into the cache memory and use it inside, replace it according to, this depends on the line replacing algorithm itself. Okay, so example of a memory address. So this one is representing memory address. Okay, so memory size of 1 megabyte, 20 address bits, addressable to the individual byte. Cache size is 1K lines, each holding 8 bytes. Okay, so here we have around 20 bit, 20 address bits. So within the 20 address bit, we have 7 bit that representing tag, 10 bit representing line, and 3 bits representing word. So imagine that, okay, where is the byte stored at main memory location A, B, C, D, E stored. So the A, B, C, D, E tag ID is 55, line ID is 39B, word ID is 6. So this is representing the information according to this memory address. Okay, so that's all for today. I will continue with our third part under memory organization later. Hopefully, this will be useful for you. I'll see you guys in my next video. Thank you for the likes and subscribe. So next time we will look into memory organization. So stay safe, stay healthy, and take care. Bye bye.